Today's lecture is going to be very interesting because we're going to do some applications. And this is applications in quotation marks. This is not real world applications. This is applications to other areas of mathematics. So applications to other, you can say, non-topology areas of mathematics. So occasionally in different fields of mathematics, you might borrow a theorem or some kind of result that is otherwise proven through a topological approach. And I'm going to show you 3 theorems that they feel very similar, but they're quite different. So there's 3 similar feeling theorems, different. And we're going to go through the following. We're first going to talk about something called Brouwer's fixed point theorem. Then we'll talk about the Boursac-Ulam theorem. And then third, and I think I'll put this on the homework, I find this to be the least interesting of these 3 theorems, though maybe there's someone out there who's a lot more enthusiastic about it and maybe can show some more interesting consequences of it. This is called the theorem of the hairy ball. So here's what we'll do is we discussed these 2 theorems in Topology A. So those of you who have attended the first semester course in topology, we have seen those theorems, but we've only proved them in dimension 2. We did not have the tools to prove them in higher dimensions. So you've seen them. Now I think out of these theorems, the one that is by far the most interesting is the Boursac-Ulam theorem. This is the most interesting one. And if you're interested, there is a video called Boursac-Ulam that proves it in dimension 2. It states it in a more general way, and it uses it to prove what is known as the ham sandwich theorem, which is a very surprising theorem in geometry. And then we solve a problem in combinatorics called Nesser's conjecture through the Boursac-Ulam theorem. So very surprising uses of this theorem in mathematics. We're not going to talk about any of those uses because we already have a video on that. And for those of you who are interested, you can just reference that and look at that. We're just going to be focused on how you prove it, not how you use it, how you prove it. But we're first going to start with Brouwer's fixed point theorem. We proved this theorem in Topology A, and we proved it using the fundamental group. And what you're going to see is going to be something very interesting. The proof of Brouwer's fixed point theorem in general is going to be almost the same identical proof, almost the same identical method, but it's just going to use homology instead of the fundamental group. So we're going to start with this one. Now I should give you a slight warning. So today's lecture is very what we call ad hoc. So a lot of the arguments are clever tricks out of nowhere. They're almost magical tricks that are not very inspiring, especially when we get to the proof of the Boursac-Ulam theorem. That is just ad hocness to the ultimate degree. But maybe if you're one of those people who love these ridiculous arguments out of nowhere, then maybe you'll enjoy this lecture more than other ones. I'm not a fan of ad hoc arguments. I feel like if you truly understand mathematics, you can trivialize it, you can motivate it. If it's a trick out of nowhere, all that tells you is you know that it is true, but you're not seeing why it is true on a deeper level. But anyway, let's go through these theorems. So like I said, we'll focus on the first 2. Maybe I'll put the third one on the homework. And we'll start with the first one. This is the easiest one, and it's quite interesting. So this is Brouwer's fixed point theorem. And it says, okay, so this is the theorem. Let Dn be the n-dimensional closed disk. You can say unit disk, does not matter. And you're going to say that if F is a map from the disk to itself, is continuous, there is a point, at least one, so that f of p is equal to p. So that's what we call a fixed point. So here's something interesting. Note, if n is equal to 1, then you're talking about a continuous function from the closed interval to the closed interval, because the closed interval, that's just homeomorphic to the closed disk. And this case, this special case, can be proven using the intermediate value theorem. So you do not need any fancy topology to prove it. And you can think about this. I actually give this type of problem as a homework problem, sometimes as an exam problem in advanced calculus. It's a few lines. And n is equal to 2 was proven in the first semester course. To prove it more generally, we're going to use homology. And here's how the proof goes. It's the same identical proof if you've seen the old proof. It's the same identical proof. It uses something called the no retraction lemma. So this is called the no retraction lemma. Here's how it goes. A retraction is a map, let's call it R. Let's say from D2, well, from Dn, from the n-dimensional disk to its boundary, s minus 1. So we're going to assume that n is at least 2. And this should make sense, right? D2, that's the two-dimensional disk, and S1 would be its boundary. So the boundary is a subset of D2, but its dimension is 1 less. So this, even though this might look funny, this is actually correct. So a retraction is a continuous map so that R of x is equal to x for all x in the disk. For all x on the boundary. So the boundary does not move. Now, the reason why it's called the retraction is I like to think of a telescope. So if you have some kind of telescope, which has segments which extend out, this is sort of like the base of the telescope. And you're saying that you can retract back the telescope. So all of these segments, they move back, and the base stays fixed. So you're saying that if you have let's say a two-dimensional disk, you're mapping the points to the base, but the base itself, it stays fixed. It never moves. So you have this kind of situation. And the lemma says is, but there is no retraction. A retraction does not exist. So you can define it, but it's an empty concept. There's no such thing as a retraction map. And by the way, let me just say that if this was a punctured disk, then you can certainly do that. If you had a puncture in the middle, all you have to do is you just kind of map everything out with rays like this. And because you're staying away from the origin, it does not pose itself to be any kind of problem. There's no discontinuity there. But when you include the entire disk, then you start having problems. Okay, so here's the proof of Brouwer's fixed point theorem. So here's theorem. I'm going to say this again. If f is a function from Dn to Dn, then there is a point P in Dn with f of P is equal to itself. there's at least one point. By A, there could be only one point. So if you take, for instance, the two-dimensional disk, if you were to rotate this by a certain amount, then the only point that stays fixed is the origin. So there's at least one, and sometimes there can only be one, but there's at least one. Another thing I would like to say is, so there's like you can say an interesting consequence of this is, so let's say you have like a bowl of soup, okay? And on the surface of the bowl of soup, you have like an alphabet, like alphabet soup. You have an A, you have a B, you have a C, you have different letters, then you have uppercase letters and lowercase letters. So you have different kinds of letters, and you have so many letters that they pretty much completely exhaust the entire surface of the bowl. And then you put a spoon in there and you mix it around, so you're doing some kind of continuous transformation. So you move it around so the letters all move around. And what you're saying is if you had a before picture and then you have an after picture, you will be able to find at least one letter that did not move. Maybe the other ones move, but there will be at least one that did not move. So that's a pretty surprising result that it says. And like I said, it has consequences to other areas of mathematics. I'm going to put an interesting question on the homework. It says something about non-negative matrices. So that's an interesting consequence to linear algebra, but I'll just put it on the homework and it will follow from Brouwer's fixed point theorem. Also, it's actually important that this is a closed disk. If it's not a closed disk, then it's not going to be true, because the open disk, right? The open disk. So let's write it like this: the open disk is actually homeomorphic to Rn. So you're saying if you have a map from Rn to Rn, is there a fixed point? And the answer is clearly not. You can take any translation. A translation will move around Rn, but there's not going to be a fixed point. So it's actually important that it's a closed disk. So here's the proof. And it's a very nice proof. It goes like this. It's a proof by contradiction. So you're going to say, suppose that for any x in Dn, we have that f of x is not equal to x. So we're going to construct the map, and we're going to call this map R for obvious reasons, because we're going to construct a retraction mapping. We're going to contradict the no retraction lemma, and then from here, Brouwer's fixed point theorem will immediately follow. So from Dn to Sn minus 1, and this is the way we do it. So here's a picture for what we're doing. So this is Dn. We're just going to pretend it's D2, but this is, of course, more general. And you have a point somewhere in Dn. Let's say this is your point x. And then f of x is not equal to x. So it has to be somewhere else. Somewhere else. It has to be f of x. And I always forget which way it goes. You can draw a ray that begins at f of x, goes through x, and it ends up over there. Or you can do it the other way around. You can start at x, go to f of x, and lands over there. So I'm not sure which way it goes. I'm going to take a guess. If it's not correct, it's not going to work, and then it's the other one. So I'm going to take a guess that we're going from x to f of x. So we're going to construct the map, this map, in the following way. So R of x, this is going to be, so this is the way we're going to do it. We're going to start at x, we're going to go to f of x, and we see where that line hits on the circle. So this is just, you're going to extend a ray from x to f of x, and we find the point on the boundary. So that's the way that you do it. So you go from x to f of x, and you hit a point on the boundary, and that's how this R is being defined. Okay, so we claim that R from Dn to Sn minus 1 is continuous which we're not going to check. That kind of makes sense. It's just a question of how much detail you want to put. That's not the interesting part of the argument. It should make sense that if you were to take this x and you were slightly perturb it a little bit, then this f of x will slightly perturb because f is continuous, and then the ray slightly changes position. So it does make a lot of sense why the r is continuous. If you actually want to prove that it's continuous in a more rigorous way, then you will have to write out the exact formula for this. And then after you write out the exact formula, then you have to do the annoying thing of actually verifying it's continuous by maybe like a delta epsilon argument or something like that. But that's what we call missing the point. It's the idea here that matters more. So r is continuous, and it is a retraction. So that would mean that if you do r of x, that would be x if x is already on the boundary. Okay, so let's see if this works. What if x was already on the boundary? So then if x is already on the boundary, then f of x, well, it would be somewhere else. We do not know where. It does not have to be on the boundary. And then we're going to draw a ray from x to f of x. And when we draw the ray, you see what the problem is. The problem is it's not necessarily the point that we started at. So I made it, therefore you have to do it the other way. You're going to extend a ray from f of x to x. And then you find where it intersects. So really it's the correct picture with the arrow going in the other direction. And now it works out, because if you are already located on the boundary, and f of x is, let's say, over here, then when you draw the ray from f of x to x, you're already on the boundary. So the ray puts you back to where you are. So this property is satisfied. Okay, so you found the retraction. So the part that's very important, that I think maybe we should emphasize this a lot, is this. That this is very, very important, because no matter what point you pick in the disk, you have two different points. And so you can define a line, right? If you only have one point, it's not enough to define a unique line. You can define a unique line, and once you define that unique line, you get that ray, so you get that intersection on the boundary. So this is why this part is very important. So this is the proof of Brouwer's fixed point theorem. And what remains is to justify this no retraction lemma. So let's see how to do it. So proof of no retraction. So we're going to assume that we have a map from Dn to Sn minus 1, so that r of x is x for all x on the boundary circle. And then from here we'll get the contradiction. So look at this commutative diagram. This is going to be r, and then we're going to take the identity map here, and then this one is going to be the inclusion. So let's see if this diagram commutes. So if you have an x, this is r of x. R of x is on the boundary, and the identity just takes it to r of x. But the inclusion map will take the r of x back to r of x. So the map does not, so then the map does not commute. Yeah, so r is supposed to go from Dn to S minus 1, so that's fine. And then there's an inclusion map. So this is a subset, right? This is a subset of that, so there's an inclusion map. So let me actually do this again. If I pick if I pick x in Dn, that goes to R of x. Okay? And then this is the identity. So this is again R of x. So this is not working out. So I have to try something else. So let's try this again. What else can we try? I guess maybe we want to use, I definitely want to use the identity somewhere. I mean, I could write this, but I mean, that's not, yeah, I mean, that one's not really giving any useful. Maybe what I want to do is I keep this as the identity and I reverse the arrow. I make the arrow go like this. Then I think that should work now. So let's see if this works out. So if I pick an x over here, that goes to x. That's inclusion. This goes to R of x. But R of x is x, because the x was on the boundary circle. So you get R of x. Yeah. So this diagram commutes. And we're going to apply the homology functor. So we're going to take the n-1 homology of this entire diagram. So these are the induced mappings. So as you can see, this is a very nice proof. Hn-1, Sn-1. This is I star. And now the closed disk is a contractible space. So this is just zero group. And this is the homology of the sphere when the homology matches the dimension. And the identity, the induced, this is just the isomorphism, right? This is just the isomorphism from the integers to the integers. And this diagram is supposed to commute. Well, I mean, here's the problem. This arrow takes you from the integers to the integers. So if you pick the generator, it's supposed to map 1 to 1. But this arrow commutes with this. But this arrow sends you to 0, right? This arrow sends you to 0. And then 0 goes to 0. So 1 goes to 0. So this contradicts the fact that the diagram commutes. So you can see this is a truly very clever proof that just took advantage of homology. And then, I mean, we call this ad hoc. It's very simple, but it's not something one would typically think of in the beginning. But that's the proof. That's the contradiction. So if you assume that you have this, then from that diagram, you have this contradictory diagram. And so that means that retractions from the closed disk to the boundary, they cannot exist. Now, the next theorem that we want to talk about is Boursac-Ulam. But before we talk about Boursac-Ulam, what I wanted to say, and I should have said this earlier, this is probably should have been the first thing I should have said. It was basically this, that it's going to be a very funny looking theorem that Rn is homeomorphic to Rm if and only if n and m are the same. Now, if they're the same, well, the converse is completely trivial. The part which is interesting is, why is it that different dimensions of Euclidean spaces are not homeomorphic to each other? And this is like a great illustration that it feels like you can prove this using first principles. So in other words, just by using the definition of a homeomorphism and nothing more, but I'm not sure how to do it. maybe someone has a way to do it, but if someone does have a way, it would be unbelievably complicated, but is not doable. Or maybe it is doable, but then it's like super hard. I've never seen it done directly. Like, it's such an easy statement to understand. You're saying that you cannot find a bijection between Rn and Rm that is continuous and whose inverse is continuous. So it just feels like you should be able to just apply the definitions of continuity and get some kind of contradiction out of it, but I've never seen it done. And this is like one of those themes in mathematics that apparently you actually need extra tools in order to solve this, that you cannot just do this directly. It's like, if you want to use like a very extreme example of this, the Poincare conjecture, it's very easy to understand as a problem in topology, but there's no direct way to prove it. You have to just do something totally, completely different. One has to do PDEs on manifolds and various results on that to reach the Poincare conjecture. So it's not that it follows directly. There's completely other stuff that's going on that just eventually leads to it. So this is what makes it interesting. Now, another interesting thing that I want to mention here is it is possible to prove this directly if you replace the word homeomorphism by the word diffeomorphism. Diffeomorphism is basically the same thing, but you're now assuming that your maps are differentiable, whatever that means. And actually, later on in this course, we're going to be talking about manifolds. And when we talk about manifolds, we will define what it means to be a diffeomorphism. Okay, so it is actually possible to prove this in a very direct way without using anything fancy. But when it comes to showing it's not homeomorphic, that is substantially harder. And the proof will use homology. So now let's present the proof of this. It's actually a very nice proof. It's very clever. It's a very short proof, but it's not something that one would typically first think of. It uses a trick that if you've seen before, you can replicate it, but when you see it for your first time, it's not something that immediately comes to mind. So you're going to assume that you have a homeomorphism is a homeomorphism. And you're going to pick a point in Rn, and you're going to set Q to be its image point. So then F restricts to a homeomorphism when you delete the points, which I'm going to call F again, abusing notation. Take away P to Rm, take away Q. Right, because there's only one point that maps to Q, and that's P, because it's a homeomorphism, it's a bijection. So when you remove it, you then have a bijection between this set and that set that's furthermore continuous and all of that, because the original F was continuous. So you now have a homeomorphism. So thus, F induces, so now you pass to homology, F induces an isomorphism between the homology of punctured n space with the nth homology of punctured m space. Okay, but Rn take away a point is homotopy equivalent, and we talked about this many times before. It's homotopy equivalent to the sphere. Right, so if you take the two-dimensional plane and you remove a point, the punctured plane is homotopy equivalent to the circle. It's the same kind of argument. So so basically, you can say that one has an isomorphism between the nth homology group with Sn. There's a isomorphism with the nth homology group of Sm, because this is M. But this is Z. But what is this? Well, this one, there's two cases. This one is either Z if n and m are equal, and it's 0 if otherwise. I mean, it would be Z again if n is 0, but we're not considering that case. So it only gives you Z when they're the same. So the only way you can recover the group of integers is when the n and the m are the same. So the m has to be n, and that's the proof. So it's a very nice proof, but you have to use homology in order to do it. It just does not follow directly. The next theorem that we're going to discuss is perhaps the most interesting one, and it is certainly the most useful one. And this is what we call the Borsuk-Ulam theorem. And it says that if f is a continuous function from the n sphere into Rn, then we can find a point on the sphere so that f of p is equal to f of negative p. So the function assigns an n vector for every point on the sphere, and Borsuk-Ulam theorem says that no matter what function you have, there will always be antipodal points on the sphere that get mapped to the same n vector. So as an interesting consequence of this, as a consequence, what you can do is you can consider a map from S2 into R2. So you think of S2 as representing the Earth, and R2, well, it's a 2 vector, so you can have the first component represent the temperature at every point, and the second component is, you can say, is the, let's say, the air pressure. Or maybe more interestingly, let's say the humidity. Or actually, how about this? How about the altitude? The altitude above sea level. So this is a continuous function, though maybe using the altitude is not the best, because the altitude might not be continuous. If there's like a building and then it suddenly stops and it continues, then you have that discontinuity in the altitude. There's a sudden drop in altitude. So that would not be a continuous function. You need something that varies continuously. So let's just say humidity at every point. So you have a function, and what this says that at each moment there are at least one point, one location on Earth where the temperature and humidity is the same at its opposite point. So you have your Earth, and you're saying somewhere on the Earth at every moment, wherever you're located, well, I should not say wherever you're located. I'm just saying there's some location, and the antipodal point on the other side of the world that will have the same temperature and the same humidity. So if I told you they have the same temperature, that alone is already surprising. But we're saying even more than that, that not only do they have the same temperature, they also have the same humidity on top of that. And those of you who have taken, so you can say in Topology A, that's the first semester course in topology, we proved this for n is equal to 2. And for n is equal to 1, this is just the intermediate value theorem in disguise. It just follows from the intermediate value theorem. So you're saying that if you're mapping the circle to the real line, there's 2 points in the circle that must get mapped to the same point on the real line. And that is just a consequence of the intermediate value theorem. And in topology A, we proved this for n is equal to 2. What we did is we used winding numbers to do that. And the proof was quite nice. It was not too bad. However, proving this theorem in general is extremely hard. This is amazingly very hard to prove in general, and the proof for n is equal to 2 does not actually generalize. Well, that's the thing. Actually, you could try to generalize the proof. So if you're interested, you can just look at the previous lectures from the first topology course, and you can look at the lecture that's called Boursac-Ulam theorem, and you can see how you prove it for n is equal to 2. But if you try to generalize that proof for a general n, it's just not going to work. There's some complications that arise. You could make it work, but filling in those gaps is harder than proving it directly. So there are some books that prove this theorem using very advanced machinery of cohomology or other things, and we do not have access to that kind of machinery. So we're going to have to prove it in a different way. And out of different sources that I've looked, I think the nicest proof, we're going to follow the proof given in Breton. I think Breton gives the nicest proof of this because his proof only uses homology. It uses things that we already talked about before. So I think it fits nicely with the theme of our class. The other books, their proofs, like if you look at some of the other books on algebraic topology, they put the proof of Boursac-Ulam towards the very end of the book because they use advanced machinery. And we do not want to do that. So let's discuss this, but I have to give you a warning. This proof is ad hoc overload. So if you thought that the proof for Brouwer's fixed point theorem was clever, but it's sort of like an ad hoc type of an argument, wait until you see this one. This one is just completely out of nowhere. It's just going to take you by surprise. So here's what we're going to do. So we're going to assume, we're going to have the following lemma. Okay, so I'm going to make a lemma here. So the lemma is going to say this, that let's say that n is bigger than or equal to 2. I'm going to say that if f is a function from the n sphere to the n minus 1 sphere, and let me say it like this. It is impossible to have a function from the n sphere to the n minus 1 sphere so that f of negative x is equal to negative f of x for all x. That's what we're saying. It is impossible to have a function from a sphere to a lower dimensional sphere that has this property, that the function of an antipodal point, so basically if you have a point on the sphere and you look at its antipodal point, then the image of the antipodal point is always mapped to the antipodal point of the image, no matter how you do it. So that's the lemma. So this is an impossibility. And if you're willing to accept this lemma, then we have the following. So this is proof of Boursac-Ulam. So this is what I mean. This is very ad hoc. I mean, like, why would you even consider that? But it's going to follow from this lemma. So here's the proof of Boursac-Ulam. So what we would have here is we would say that, so let's say we're given a function. So let's call it g from Sn to Rn. And we want to find a point on Sn so that g of the point would be g of its antipodal point. So we're going to assume to the contrary, so we're going to do this by a proof by contradiction, to the contrary, that if you do g of x, it will never be equal to g of negative x for all x on Sn. So now we're going to construct the map, and this is going to be a continuous map from the n sphere to the n minus 1 sphere, and is going to be given by the rule that f of x is going to be g of x minus g of minus x, and then you just divide out by the norm of that vector. So let me explain what's going on over here. G of x, this is something in Rn, right? This is something in Rn, and this is something in Rn. So you're just subtracting two vectors on Rn. So this is going to be some vector in Rn. And we know that this vector is not equal to 0 because of this assumption. So this is a non-zero vector. So we're taking that vector and we're dividing out by the length of the vector. Doing so, we are normalizing the vector to have length 1. So it's a unit vector. So in particular, it's in Sn plus 1. You have to be careful. This is not Sn. The dimension is 1 less. Because whenever we talk about an n minus 1 sphere, we usually embed it like just to, if that's not clear, like for instance, S2 will consist of points x0, x1, x2 in R3 so that the sum of squares is exactly equal to 1. So notice that we usually, when we work with the 2 sphere, we usually embed it into R3. So in general, Sn minus 1, this is the embedded sphere in Rn. So that's how this works out. And so this is therefore a point on the n minus 1 sphere because we have divided it out. This is why this is important. It's non-zero. You're dividing by something that's non-zero. It's a continuous function because these are continuous functions. So this is a continuous function. And now look what happens when you replace f by negative x. And now observe that if you do f of negative x, then you get, this would be g of negative x, negative g of negative x over the same thing, but in the norm. Now, the norm is symmetric. You can interchange them, that's not a problem. But the numerator is not symmetric. If you interchange them, as you can see, it's the negative of what you have. So this is negative of f of x. But this f from Sn to Sn minus 1 contradicts the lemma. So we got the contradiction, and from this contradiction, the proof is complete. So this is proof of Boursac-Ulam. And you look at this, it looks very innocent, it looks very simple, but the difficulty, this is the entire difficulty in proving the lemma. This is the difficult part. And like I said, if you're interested to see how to prove it in the special case when n is equal to 2, by using our previous methods from our first semester course in topology, you can just look at that video for those of you who happen to be interested in that. And you can try to generalize it for what we're doing right now. But unfortunately, it does not really generalize in any straightforward way. There is a way to generalize it, but it's actually more difficult than the lemma that we're about to do. So now we're going to focus on proving this lemma. And like I said, this is going to be very ad hoc. It's going to be, the proof is going to appear as if it's out of nowhere. We're not going to prove the lemma directly. We're going to do something else first. So here's how we start. Let pi be the projection map from the n sphere to the projective plane. So the projective plane is, the way we often define the projective plane is, this is Sn modded out by G, where G is the automorphism group consisting of the identity, and A, where A is the antipodal map. It kind of makes sense why we're going into Pn, because we are working with antipodal maps in the Boursac-Ulam theorem. So that part actually kind of does make sense why it comes up. But that's probably like the only motivating part. The rest of this argument is not exactly very motivating. So this is going to be our map. This is, in fact, what we call a double sheeted covering. Actually, that's quite nice because we get to see covering spaces again. And here's what we're going to do. So we're going to say let sigma be a simplex, a d-dimensional simplex in Pn. Okay, so then sigma can be lifted to Sn. So previously, we talked about lifting paths. When we were talking about covering spaces, we talked about that if you have a path in the base, you can lift that path into the cover. And furthermore, the lifting is unique if you specify initial conditions. But if you do not specify initial conditions, then the number of different lifts that you have is determined by the sheet number, right? It's basically the number of pre-images that one has. So here we're not going to have any initial conditions. So when you lift the sigma, because this is a double covering, this is a double sheeted covering, it would mean that, i.e., we can find, let's say, sigma tilde, and that's a mapping from the D simplex to the cover, so that if you compose with the projection, you get back to sigma. It's just like lifting paths, right? You first map the simplex to the cover, and then you project it back down to the base. And the other lift is what you get when you compose with the antipodal map, right? So you can have sigma tilde composed with A, where A is the antipodal map, right? So you basically map the simplex into Sn, and then you map Sn into itself using the antipodal map, and you'll get a different mapping. But when you project it back down to Pn, that would be the same thing, because in Pn, composing with the antipodal map lands you in the same point. So that's going to be the other one. So that's the other lift. So those are the two liftings that we have. So if you find one lifting, the other lifting is just determined by composition with the antipodal map. Okay, so there's two liftings. Now, the next, I mean, you could, I guess, be a little bit bothered by the fact is, why can it be lifted? Because we talked about that paths can be lifted. So how do you know that a simplex can be lifted? But it's actually very similar to, remember we talked about how you can lift a square, right? We talked about lifting homotopy. Well, a homotopy is basically a two-dimensional simplex, and sort of the same argument. You just triangulate it into small pieces, and each of the small pieces can be lifted. Okay, so this is the lifting part. And what I want to do next is I want to define the following morphism. So actually, let's come up with the following definition. And like I said, this is very ad hoc. So let d be an integer bigger than or equal to 0. This is supposed to represent the dimension. So we know that when you talk about CD of Sn, this is the D chains in Sn. So what are those? This is the free abelian group generated by all simplices. And when we say simplices, we technically mean mappings from the D simplex into Sn. So that's what it is. That's what we call D-dimensional chains. So now we're going to do something that's a little bit unusual. We're going to define almost the same thing, and I'm going to put a bar over it. And this is going to be the group. And notice I'm no longer saying it's the free abelian group. It's going to be the group generated by all simplices, just like before. But, and this is the difference, but whose coefficients are no longer integers. Okay, so they're not going to be integers. They're not going to be integers. Instead, they're going to be integers mod 2. So to make sure that we understand what we're saying, so if you have a chain, so this is how a chain is going to look like. So a chain in this group will look like this. So C would be a formal sum. So you'll have A1, sigma 1 plus A2, sigma 2, and so on, where every sigma is going to be a mapping from the D simplex into Sn. But every coefficient, instead of being an integer, is going to be an integer mod 2. Okay? So in particular, C has no repeating simplices. Why not? Well, because if you have, let's say, sigma I plus sigma I, that will become 0. It becomes 0 because this is sort of like the coefficient here is really 1 mod 2, and the coefficient here is 1 mod 2. So if two simplices are repeating in this formal sum, then you just make it 0. So you can think of this as a list. So I think maybe this is like an intuitive way of interpreting this. A chain, we write it as a formal sum, but it's really an unordered list of simplices. And when you're working mod 2, you're essentially saying that it's a list without repetitions. So there's no repetitions in the list. And furthermore, maybe this is also helpful, sigma would be equal to negative sigma, because 1 is congruent to negative 1 mod 2. So in particular, C has no signs. It has no negative signs, because if you have a negative sign, you can just make it positive. So it's, in some sense, this is a very simplistic type of chain where there's no orientation, there's no positive or negative, and there's no repetition. So it's actually simpler. And for those of you who are interested, we are about to introduce a simplified theory of homology called mod 2 homology. That's what we're going to be doing. It's going to be just like regular homology, but it's going to be simplified. You do not have to worry about negative signs or anything like that. And sometimes it makes things easier. But the price to pay is you do lose information. You are losing information. But the advantage is sometimes by using this approach, you could make some calculations simpler. It's like a theme in mathematics that sometimes when you want to prove something, if you focus on something less, it becomes easier to prove. That's kind of what it is, because when you try to focus on everything, maybe there's too much information to keep track of. And this mod 2 homology theory, it gets rid of some of that information, and it sometimes makes things easier. Okay, so this is the way we define. So let's remove this. So we define C D bar. So this is sort of like the bar just represents, it's just like chains, but everything is mod 2. We define this, and this is also going to be similar. This is Pn. That's going to be similar. So we've defined these two groups. So the next thing that I want to do is we will define, so there is an obvious map, an obvious homomorphism. When I say map, I mean homomorphism, of course, that takes us from a d-dimensional chain in the sphere to the d-dimensional chain in projective space. And the way you do it is just by composition. So if you have a simplex, so in order to define this homomorphism, it's sufficient to define it on the generators, which are the simplices. So you take one of those simplices, and the way you map it in the projective plane is just by composition. So if you compose it, then you get, I think I did this incorrectly. I meant to say sigma first and then composed, right? So let's see if I'm doing it correctly. So you're going from delta n to Sn, that's sigma, and then you're going into Pn by pi. So I actually did it incorrectly. So sigma composed pi, like that. So that will give you a simplex. I meant to say delta D, but I'm sure you understood that. So there's an obvious map from this one to this one. But there is another map. There is another morphism that goes the other way around, from Pn to Sn. And I'm going to call this morphism, let's give this morphism a name. So this one, you can call this one pi, because it comes from the projection. We are, of course, abusing notation. You can maybe call it pi star or something. I'm just going to call it pi, just to indicate that you're using the projection from Sn to pi n to create this. And this one, I'm going to call this one lambda. So lambda will stand for lifting. This is the one that's going to come from the lifting. And the way you do this is you're going to pick a simplex in here. And we said that every simplex can be lifted. It can be lifted to this one. So you see, the issue is, how do you, like, which one do you pick? Because there's two. Which one do you pick? So this is going to be the clever part. We're going to pick both. So we're just going to take the sum of both. So we're going to take sigma tilde, and the other one is with the antipodal map. So am I doing this correctly? Yes, right, with the antipodal map. Because then it does not matter, because if you were to, I mean, I'm basically saying this, there's two liftings. There's sigma, and then there's sigma tilde prime. And you pick one, it does not matter, and then the other one is the antipodal map of that one. And if you happen to pick the wrong one, it's not going to matter, because the other one will be, because if you're doing the antipodal map twice, you get back to where you are. Okay, so if you take the antipodal map of that, you just get back to the other one. So it does not, you cannot pick the wrong one, because you're picking both of them. That's what it is. So this is going to be, we're going to call this one lambda. This is the lifting morphism. It lifts a simplex into the two that lift in this one. So that's how lambda is being defined. And now we're going to get an exact sequence out of this. So we're going to have, so behold, now we just not too long ago talked about exact sequences. So I think this is quite nice that they come up again. So behold, we have an exact sequence. So you can go from this one, using lambda, into this one, chains in the sphere. And then from chains in the sphere, you can go with pi, with the projection, back to chains in projective space. And this is going to be a short exact sequence. So this is a short exact sequence. So let's actually check that this is a short exact sequence. So we have to check that there's a 0 over here. So this means this has to be injective. So this part makes sense, because if you have a different sigma, then these will be different, right? So you're just getting different. So it's injective. Why is this surjective? Well, it's actually quite simple why this is surjective, because if you give me a simplex in here, I can lift it to over there. So that's not a problem, okay? So the interesting part that we have to ask is we have to show why the kernel of pi is actually equal to the image of lambda. So again, so that's really the interesting part over here. So let's say, okay, so say that you have a chain in the one in the middle. And pi of c is equal to 0. So then it means, now let's write. So we're going to write, now how does a chain look like? So here's how a chain looks like. A chain is a formal sum of simplices, but because we're working mod 2, there's not going to be any repetition, and we can just assume that all of the signs are positive. So we're just going to have sigma 1 plus sigma 2 plus sigma 3 and so on. Right? There's no repetition. They're all different. And we're saying that when you take pi of c, so pi of c, this is just the abused notation map. That's just applying the composition to each of those. So you have pi composed sigma 1 plus pi composed sigma 2 plus pi composed sigma 3 and so on. So if it becomes 0, how does it become 0? It becomes 0 if there's cancellation. If, for instance, this one repeats twice, right? It has to repeat. So pi 1 has to repeat somewhere else. So there has to be something else, pi composed, let's say sigma I, that these become exactly the same. These are exactly the same, right? They're the same. So sigma 1 and sigma I are different, but when you compose them, they become the same. And then, so you have double repetitions. Now, why does this matter? So the reason why it matters, so then, if we let pi composed sigma 1, so then here's what it means. That it means that when you lift, it lifts to sigma 1 and sigma I, right? That's what it means. So this one lifts, and it's the same thing with the other one because they're equal, right? They both lift. I mean, I should not say both because you only have really one of them, but those are the liftings. So what's the issue here? Well, the issue is basically this. Now, let me just zoom out a little bit to make it a little bit easier to see. If you take, so you have to find, you see, you're saying kernel is equal to the image. So the kernel vanishes. So something is 0, and we have to find something in here so that lambda applied to that something will give us the chain. And how do we do it? Well, we take this one, pi composed sigma 1, and when you apply lambda, this is the lifting morphism. So it's going to give you sigma 1 plus sigma I. It's going to give you the two liftings. And the point is that if you have a chain whose kernel is 0, then all of those pairs that cancel out under the projection, they come from that lifted, it's the lifting of that map that they both project to. And so this is why this is an exact sequence. Okay, so, and now look at this. So this next part is going to be very cool. So let's move this away. So we have the following exact sequence. We have this one. We have this thing that we're calling lambda, CD SN, CD pi n, I'm sorry, Pn pi. This is an exact sequence, and this is exact for all D. And furthermore, these form chain complexes. So, right, we have chain complexes. We just go down to CD minus 1, CD minus 1, CD minus 1 of the same thing, and so on. And because of this, we have, these are chain, like the maps that are going down, they form chain complexes. And we have a short exact sequence of chain complexes. So basically I'm saying this, we have a short exact sequence of chain complexes. We have CD, pi n, we have this one. So when we talked about homological algebra, we talked about these things called chain complexes, and how every time you have a chain complex, you can talk about its homology. And furthermore, that if you have a short exact sequence of chain complexes, then from that short exact sequence, you can create a sequence, an exact sequence in homology by using what we call the zigzag lemma. So we used the zigzag lemma to create the Meyer-Vitora sequence, but now we're doing something a little bit different. So by the zigzag lemma, we get an exact sequence in homology. So everything that we're doing right now is really cool. Unfortunately, it's not exactly very motivating, but you are using some very cool math. So you are getting this homology, and I'm going to call this homology sequence H with a bar D. This is what we call the mod 2 homology. It's just like regular homology, but you work mod 2. So mod 2 homology, so you would have, let's say, this one, Pn, then you go, so this morphism induces a morphism on that one, so that would be H D Sn. Then you have H D Pn again. And then by zigzagging, when you right? You kind of go like this, zigzagging if you return back, but when you return back, you lower the dimension. So then one has h d minus 1 pn like this. So this is the homology exact sequence that we get. And what's going to be interesting is we actually do not even need to understand these maps whatsoever in what follows. Knowing that it is an exact sequence would be completely sufficient for our purposes. For those of you who are interested, sometimes people write this as the homology of Pn, and then they put semicolon z mod 2z. I think that notation just takes up way too much space, so I just make it easier and just write that. But that's usually the way people write it. And some of you might be thinking, well, if you can work mod 2, can you really work like more generally, where you replace, let's say, the integers by the rational numbers or by the real numbers, or more generally by a commutative ring? And you can, of course, do that. But here we're just doing it mod 2. And if you're interested about what this means is, like to make it, maybe make it a little bit more concrete, you would just say that this is the group, right? This is the group of all d cycles in Sn, right? It's just d cycles in Sn. It means the exact same thing. The only distinction is that in this homology, when you add mod 2. So you have a cycle, and you add the cycle to itself, then you will get 0. So that would be the only distinction, that the coefficients are taken mod 2, but it means exactly the same thing. Homology is the group of cycles. It's the group of cycles, and then two cycles are treated as the same if their difference is the boundary of something that comes from one dimension higher. But it means exactly the same thing. The only distinction here is when you add the cycles, if the coefficients, they're just being added mod 2. That's the only difference. Okay, so we have this exact sequence, and here is what is going to follow next. So maybe we should remove this. Well, no, let's keep it. Let's keep it on the board and see what happens. So let's go to the largest dimension. Yeah, so let me take it away. So let me remove this, and let's go to the highest dimension that we see. So the highest dimension that we have is Hn of Pn. Because the one that will precede it would be Hn plus 1 of Pn. And because this is a space of dimension n, you're not going to have n plus 1 simplices. So all of the homology groups that go before that would all be equal to 0. Okay, so all of them will be, so we know they all have to be 0. So this is like the largest one that is possibly non-trivial. All of the other ones are definitely trivial. And then we have Hn of Sn. Then we have, you can say this is a lambda star, that's the induced map, but I do not think we even need that here. So let me just make this observation, that this proof is inspired by Breton. So if you look in the Breton book, that's what he does. But his proof is a lot more general, and it's also a lot more complicated. So I was looking through his proof, and I'm just rewriting it in a substantially much more simplified manner. A lot of the things that he does is not general. I'm sorry, it's not necessary for our purposes. He's just being more general, but we do not need that. So we have this, and then we have Hn Pn. Then we have the lowering of dimension morphism, Hn minus 1, Pn minus 1. Then we have Hn minus 1, Hn minus 1, Sn. And we have Hn minus 1, Pn minus 1. We have lowering of dimension, n minus 2, Pn minus 1, and so on, like that. Now, here's a fact that we need. We need to know the following fact. So this is the homology. This is the homology of the sphere mod 2. So the d-dimensional homology of the n-sphere is z if d is 0 or n, and it's 0 if otherwise. And you can show, and it's actually not difficult. The way you can do this is you can do this by using the Meyer-Vitora sequence. The Meyer-Vitora sequence, it works for mod 2 homology just fine. It's almost the exact same proof. It just copies almost word for word. So the only, like notation-wise, the only difference would be instead of writing C's and H's, you just put a bar over the whole thing. So the mod 2 homology would be the same thing, but instead of Z, it's Z mod 2. It's the exact same proof. So that's what we need to know. Okay, so we're going to use this fact. So let's fill this in. So these are zeros. Let me get rid of these zeros. They're just going to get in the way. Let me get rid of these zeros. So I'll slide it over so we have more space. And let's fill this in. So the only one that we're going to fill in is, I'm going to, because I do not have the tail over here, let's not focus on the tail for the time being. Let's fill in the one where the dimension of the homology matches the sphere. So this one is going to be Z mod 2. So this is Z mod 2. Okay, so we have that one. The other ones are going to be 0. This one is going to be 0. Of course, unless n is equal to 1. I'm sure we all understand that. But if n is bigger, if n is larger than 1, then this is going to be 0. And the next one, that would be a sphere. That would also be 0. Okay, so let's just remove this. This is now getting in the way. We do not want this anymore. Okay, now this is the part that's going to get very interesting. We have these morphisms, and we're going to use the exactness of the sequence to figure out what these are. So even though we do not know what these morphisms are, the funny part is we can still figure out what the groups are by just the exactness of the sequence alone. So that part is pretty cool. So let's start with this one. Maybe just to make it a little bit easier, let's call this map F. Okay, we call this map F. So because this is an exact sequence, the image of F is going to be the kernel, of that. Kernel. No, sorry about that. It makes no sense. The kernel of F, right? The kernel of the outgoing map is the image of the incoming map, but this is 0, so that's just 0. So that is an injection. Okay, so this means this is an injection. Okay, this F is an injection. Maybe I'll write it like this. So usually we write an injection by putting a hook over here. Now, okay, it's an injection. Now look at this. You have some group over here. You do not know what it is. And you have a group over here. This group cannot be 0. So let's say for a moment this was 0. And let's say for a moment this was 0. You're going to have a problem. The problem would be is that so you have a mapping. This map going from Z mod 2 to 0, the kernel of this map, right? The kernel of this map would be everything, right? It would be everything. And then it would mean that the F would be, its image would be the kernel. So you would have an isomorphism between 0 and Z mod 2. So that's why that's impossible. Okay, so if that bothers you, let's call this map G. Okay, so then it would mean the kernel of G would be the image of f, but the image of f is 0 because we're assuming temporarily for the time being that this is 0. But then you're saying that you can inject, there's an injection of z mod 2 into 0, and that's a contradiction. That's impossible. You cannot inject that into 0. So what this means is that this group cannot be trivial. Now here's the part that makes this pretty funny. So this is not trivial. This is non-trivial. So it must be z mod 2. Why? Because that's an injection. This is a group of 2 elements. So the only way you can inject a group into it is if this group has either 1 element or 2 elements. Cannot be 0 elements. I'm sorry, cannot have a 1 element, right? The trivial group. So it has to be z mod 2. That's the only possibility. So in particular, it means that this map that we have over here is actually an isomorphism. So we'll write it like this. So we can therefore say that this is z mod 2, and this arrow is an isomorphism. You want to be very careful over here. Just because the same group appears twice does not automatically mean that this is an isomorphism, because it could be the 0 map. But the reason why we know it's an isomorphism, well, because we said this is an injection. So it maps this injectively to that, but because it's the same thing, it's an isomorphism. Now, here's the next part. We claim that this is the 0 map, but that's not easy to see. So, okay, we know that therefore this is z mod 2. Okay, we know this is z mod 2. And let's give this map a name. Let's give this map f. This is 0 because this is just the homology of the sphere, n minus 1 of the sphere, assuming that this n minus 1 is not 0 itself. So we're not at the end of the sequence. So we have a 0 over here. So this mapping is the 0 mapping. Maybe what we should do is, I'm thinking probably give these names. Maybe call this G, maybe call this H, and use the exactness of the sequence. So H is the 0 map, right? So the kernel of H is 0. Kernel of H is, yeah, this is the, I'm sorry, what I said made no sense. The kernel of H is everything. Because this is the 0 map. So the image of G has to be everything. So that means this G is a, surjection. So we usually indicate a surjection by like a double, if you've ever seen it before, usually put a double arrow to say this is a surjection. So G is a surjection, so we know that. Okay, so now what happens next? So the next thing we can say is, so we said something about the kernel of H, right? This is the 0 map. We said this is an isomorphism. What can we say about the image of F, I'm sorry, the image of F? So that would be the kernel of G. The kernel of G. The issue is we do not really know anything about the kernel of G. So here, what we need to actually realize is the image, the kernel of F. So we have to look at one more. We have to look at the kernel of F. The kernel of this F is the image of this previous map. But this previous map is an isomorphism, so this is actually everything. It's z mod 2z. It gives you everything. So the kernel of F is everything, which means that this F is actually the 0 map. That's what that means. So it's the zero map. So the image of F is therefore 0. Okay, so then the kernel of G is 0, which will mean that now we said that this is a surjection, but now we're saying it's also injection. So we actually have an isomorphism over here. So we have an isomorphism. That lowers, so the lowering of dimension is an isomorphism. So now we can remove all of this because it's just getting in the way. And now we simply repeat the argument basically all over again. So we have 0, we have z mod 2, z mod 2. Yeah, we kind of have this. And then you just sort of repeat the argument all over again. It's not the perfect analogy because we also took advantage that this was z mod 2, but it's basically the same procedure. We have a 0 again. And so this one, well, we said that we have an isomorphism with that one. So this is going to be z mod 2z. And this one is therefore z mod 2z. And you can repeat the argument all over again. That you have a 0, z mod 2z, and instead of having Sn, you rather have the lowering of dimension morphism, but a similar kind of argument will show why this has to be an isomorphism, because the one after that, if you were to write the next one would actually be 0, because that would be the sphere, the homology of the sphere. So you have two zeros, like this, two zeros right next to each other, and the lowering of dimension would therefore be an isomorphism. And from that point on, you repeat. So quite basically, this is what we have. So to summarize, the relevant part of the sequence starts at the highest possible dimension. And then we go to H. We go to H n of the sphere. Then we go to H n of Pn. Then we lower the dimension. Then we go to the sphere again. Then we go to the projective space, lower the dimension, like this. And this is how the sequence is computed. So the first one is z mod 2. This 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 is going to be 0. So the spheres will give you 0. This is z mod 2. This is z mod 2. The next one is going to be 0 because you're going to get the sphere again. And then we've said that this map is an isomorphism, whereas this map is the 0 map. This map is an isomorphism. This is the 0 map. This is the 0 map. This map is an isomorphism. And it alternates like this. So it alternates between isomorphism 0, isomorphism 0, and so on. And this is basically the way that this works. So in particular, if you were to calculate the d-dimensional homology of Pn with coefficients mod 2, then this would be equal to z mod 2 for all d between 0 and n. So you can see the answer is a lot more simplified. When we talked about homology, like regular homology of projective space, it was more complicated. Like there were like different cases depending where you were. But this one works out in a much nicer way. And now we can use this to prove the lemma. Okay, so this is the summary of the result. This is what we get from the homology sequence. So if we're willing to accept this, now we can go ahead and prove the lemma that we're after. It would be helpful to write down the lemma again. So the lemma says there is no continuous map from the n-dimensional sphere to the n-1 dimensional sphere, so that if you do f of negative x, you get negative f of x. And here we're assuming that n is at least 2. So we're going to rewrite this a little bit. And the way we're going to rewrite this is, when you take the negative of a point on the sphere, you're just using the antipodal map. So you can kind of rewrite it as a commutative diagram. You have your f, you have your f like this, and then you have your f like this. Then you have A, which is the antipodal map, and I'm going to call this A again. So you do have two different antipodal maps, but because they're antipodal maps, I'm just going to call them A in both cases. So you're saying that if you take the antipodal map first, right, negative x, and you apply f, that's the same thing as first taking f and then applying the antipodal map. So we have that this diagram commutes. And in particular, what we get from this diagram is you can define a mapping from Pn to Pn-1 by basically doing this. You can use the f to do that. Right? We can just call this f again because it's induced by this f. If you give me a point in the projective n space, it's really an equivalence class consisting of a point and its antipodal. So the way I define the f at this point is I just write f of x. And it does not matter because f of negative x is the same thing. Well, I meant to say f of negative x would be negative f of x. So, and f of x and negative f of x, that's the same point in this projective space. So I can define a map from the n-dimensional projective plane, not projective plane, projective space to the n-1 projective space by using this f, right? I just pick a point, so there's two choices, and it does not matter what choice I pick, because regardless of what choice I pick, you have this relationship hold, right? It gives you the same, it's well defined basically. Now, okay, so here's the way we're going to use this, is to make it easier, to make the argument easier to follow, let us pretend that n is equal to 3. You're going to see that the argument that we're about to give completely generalizes to any number. I'm just picking 3 because when you write out things in the abstract, sometimes you get lost with what you're doing. You can kind of turn it into like a proof by induction. So here's the way the proof is going to go. Let's move this out of the way. You're going to start your sequence, your homology sequence, at the very end. So you start with P3. So you start with P3 because n is 3. And then you have H0 of S3 H0 of P3. So we do the boring stuff. So this one is going to be H1. Yeah, this one is going to be H1 of P3. This is going to be H1 of S3. This is going to be H1 of P3. Then we have H2 of P3. We have H. You can see if we did this in general, it's just going to be harder to see the main idea. So this is H2 of S3 and then H2 P3, H3 of P3, and probably need a few more. H3 of S3, and the one and then finally H3 of P3, like this. Okay, so that's what we have. And let's start filling in what we know. This is what we did before. This is Z mod 2. This is Z mod 2. This is Z mod 2. This one is going to be also Z mod 2. This is 0, Z mod 2, Z mod 2, 0, Z mod 2. Now these are all going to be Z mod 2 because this is the zeroth homology, so it's the number of components. So we fill this in. And more importantly, let's also say something about the mappings. So this mapping is an isomorphism. This mapping is 0. This mapping is an isomorphism. This mapping is 0. This mapping is 0 again. This mapping is an isomorphism. Because basically we saw that when you lower the dimension on projective space, you always get an isomorphism. This is going to be the 0 map. This is the 0 map. This is an isomorphism. Now this actually is an isomorphism because this is just the zeroth homology, so this is just connected components. This is the identity map, right? Connected components. And so is this. It's the zeroth homology. So we get all of that. And now we're going to do the exact same thing again. Okay, so what are we assuming? So we are assuming, so this is like a proof by contradiction, that we have a map from S3 to S2, so that if you do F composed the antipodal map, you get the antipodal map composed with F. So you basically get like a commutative diagram with the antipodal map. So we're going to write down over here another exact sequence, but this is the one that's going to be for S2 and P2. So we'll write it over here. So this is going to be H0 of P2 going to 0. This is going to be H0 of S2. This is going to be H0 of P2. This is H1 of P2. H1 of S2. H1 of P2. This is H2 of P2. We'll have H2 of S2, and then H2 of P2, and that is it. The other ones are going to be 0. So we'll stop right here. Now, we said that we have a morphism between the 3-sphere and the 2-sphere, but that morphism, it also induces a morphism from the projective 3 space to projective 2 space, for the simple reason because the F commutes with the antipodal map, so you can define a well-defined map on the projective spaces as well. And because it commutes with this diagram, it means that, so this kind of goes back to what we were saying, that if you have a morphism, a continuous map that continuous map induces, you can call it like F star, it will induce a map on the homology. So the d-dimensional homology of S3 will map to the d-dimensional homology of S2. And likewise, this map, which we're also calling F because it basically comes from that one, will be the same thing on the d-dimensional homology. And furthermore, because this square commutes, when we put these induced maps, like going like this, into that diagram, we'll have commuting squares. So these are just the induced maps that we're getting. So these are just all of those induced maps, and these squares are commuting. And let's fill these in again. So this one is going to be Zma 2, Zma 2, Zma 2, Zma 2. This is 0, Zma 2, Zma 2. This is 0, Zma 2. And just like before, oh, I made a mistake. This is supposed to be, sorry about that, this is supposed to be Zma 2. And we also have these mappings that go across like this. And we can say something about these mappings. So we said that this one is an isomorphism. This one is the zero map. This one is an isomorphism. This is the zero map, this is an isomorphism. Well, the ones at the end are isomorphisms. So these are isomorphisms. And now you're going to, this picture is going to lead to a contradiction. So the way we get a contradiction is this. So we know that this arrow is an isomorphism because this is the zeroth homology. So that's just connected components. So we know these are going to be isomorphisms. Okay, so now let's go to the first homology groups. Look at what we have. This is an isomorphism, this is an isomorphism, and this is an isomorphism. Because this is an isomorphism, you can reverse the arrow. And the map from this group to that group, it's a composition of isomorphisms. So this arrow has to be an isomorphism. This one, well, we do not really care about that one. That's 0 and that's 0, so this just has to be the zero map. We do not care about that one. And this one, we do not care about this one either. Actually, I guess this one has to be the zero map because it's a composite. Well, we do not really care about that one. Let's not worry about it. The one that we do care about is, well, actually, yeah, that's an isomorphism. This one is an isomorphism. Yes. So, okay. You see, it repeats again. We do not care about that one. That's just a zero map. But it repeats again. We already have it over here, from H1P3 to H1P2. We already have it over here. So this is an isomorphism. Yeah. So this is an isomorphism. And isomorphism. So this has to be an isomorphism also, like this. And we have this, well, we do not care about that square, but we have, yeah, so here we have it again, right? We're going from H2P3 to H2P2. So this is an isomorphism. And now we reach the contradiction. Finally, after all of that, we reach the contradiction. The contradiction is observed within this square. So when we write it out, this is what we have. We have Zma 2, that's the upper corner, going into 0, going into Zma 2, and we have an isomorphism here with Zma 2, and we have an isomorphism over here. So this is why this is a contradiction. It has everything to do with this 0. How can this, we're saying this is an isomorphism, right? Zma 2, and we've said this is an isomorphism, well, because this map is exactly right over here. But the problem is, that is 0, but this is not. And the diagram commutes, right? This diagram commutes. So we're saying we have an isomorphism from Z2 to Z2, but the problem is that it factors through that 0. right? We have the 0 over here, and it factors, you see it factors through that 0. So how can we have, it's supposed to be the 0 map, right? Everything gets mapped to 0, 0 gets mapped to 0, and then the map going back goes back to 0. So this is exactly where the contradiction is. We're supposed to have an isomorphism, but, I mean, there's no contradiction here, right? The contradiction is on the very last square. There's no contradiction here because, you see, like, if you're not like appreciating what the issue is, there's no contradiction on this square because this is 0 and that is 0. So this mapping is not an isomorphism. So you cannot reverse the arrow. You really need the very final square. So on the very final square, this arrow is reversible, right? This arrow is reversible. So you're saying that you have an isomorphism, but it factors through 0. So it's supposed to be the 0 map. And that right there is where you have the contradiction. So where did the contradiction arise from? Well, we made the assumption, right? So we have this commuting square, and this commuting square, it gives us a mapping of spheres and a mapping of projective spaces. And the commuting square, it allows us to establish these morphisms that commute with this entire diagram, and that is exactly where the contradiction arises. So hopefully you like that proof, even though it is very unmotivating. It is unbelievably convoluted, but it is a pretty cool proof.